Thank you. Thank you, Raghav. Thank you, Praveen. And thanks to the organizers of the start. Whatever Raghav has mentioned, it is an outcome of a teamwork. And I'm here today again to bring in younger minds. Like Raghav said, we need more young people taking up research in space science, not just in the chemistry part, as well as the other domains that will be covered today. In this program of ISRO Star. Right. So what you have on your screen, because I've been given the task to cover the chemistry in space science. Of course, it ranges from planet Earth to other bodies in the solar system to the interstellar medium. Time is going to be short, so we keep it now focused. Science part of it. What you see in the screen in front of you right now, you can see many solar system objects, including Earth. Yes, and you can see some of these molecules. Do you see my cursor? Let me use the laser pointer. Okay, you can see the laser pointer. Okay. Right, and you can see here, along with the solar system objects, we do have some of these molecules listed here. So we are going to look at molecules, which makes the solar system objects and so on. And behind these, you can see the deep space and the bright spots. In fact, this is the logo of our laboratory. I'd like to thank one of our team members. Currently, she's a postdoc in Leiden University, Netherlands. So she made this logo for us, which is self-explanatory, of course, because the deep space conditions and the solar system objects, whatever the molecules we are looking at, these conditions we can bring planet Earth and then we can study. That's what we do. Research laboratory. And you can see India right here. Right now we are expecting Chandrayaan 3 from our what's going on. So what we are going to do in the next 45 minutes is to travel from surface of planet Earth, or maybe a little bit on the subsurface of planet Earth, then move into first thing. What about the chemistry in the subsurface of our planet? I mean, the chemistry below our feet. So we can talk about many things, but only one important reaction we will focus for this 45 minutes, 1 hour. We look at the nitrogen fixation. The nitrogen, the atmosphere, we have plenty of nitrogen, and of course, some good amount of oxygen. But we think that oxygen is very important for us because we breathe in oxygen, which is the lifeline for us, one of the lifelines. But nitrogen is equally important because the reactions that nitrogen engages, making ammonia, which is very important for the plant growth. This is something like which is happening in front of our eyes almost every moment and so on. But we are not paying much attention to that. So the nitrogen on our plant's atmosphere is very, very important. Right. But what do you think when a subsurface reaction that is happening right here on planet Earth, can something similar happen on another planetary body? I'm not saying it's a nitrogen fixation, but what about the subsurface reaction, the other ones? Certainly, yes, that may be happening. Unless you explore them in detail, we do not know. But for example, if you take Mars, they say that some amount of methane is coming in and it has been lost. They are suggesting that the subsurface processes might be releasing some methane, which would be an indication of biological activity. So, we have to start linking whatever the chemistry we see in every part of the planet to the other parts of the solar system. This is where we begin. Then we move to the surface of the planet. Again, there are many reactions we can look at, but we again focus only on a few. We begin with the photochemistry. So the photons from the sun start this. Well, we say photons from the sun. Which part of the spectrum is very important for us? Electromagnetic spectrum. I don't want to touch the electromagnetic spectrum because most of you know about the electromagnetic spectrum and the range of wavelengths that we are using. Of course, the plants use a certain wavelength and the ingredients from our Earth's atmosphere and water from from the soil to make a molecule. I don't know whether you call it a simple or a complex molecule that releases oxygen. But in this process, it uses the photons from the sun. Okay. So now we know that the reactions are initiated by the photons, okay, that are coming through the Earth's atmosphere, from the sun to the Earth's atmosphere. And then simple molecules are turned to larger or complex molecules. Or way one approach. Okay. Here, this is a natural process. Okay? This is the photochemistry that is getting initiated. Fine. And the atmosphere plays a major role here. Why so much of nitrogen oxygen we have got? It filters incoming radiation, and part of the radiation reaches the surface. That's where the chemistry is initiated. Fine. Now, if we take an artificial uh, process, which of course is man-made, photovoltaic cell, some part of this energy that is passing through the Earth's atmosphere and then reaching the Earth's used up, and we make electrons. That's electricity. Okay? The absorption energy by a molecule can lead to chemical reactions. At the same time, you can have certain artificially made products that can be used where chemical reactions does not happen. Rather, you get some of this conversion of the photons to the electrons. The energy is converted from one form to the other. But the question is, if you take this solar cell, because right now we are looking at the surface of the Earth, okay? The question is, if you take this solar cell to different altitudes on the Earth's atmosphere, will it work? Yes. We'll be still getting electron. We'll be still making electricity. If we take it further away from the Earth's atmosphere, will it work? Of course, yes. And will it be working on the moon surface? Certainly, yes. That's what our Chandrayaan 3 we are going to look at the solar cells operating on the surface of the moon. Okay. So this is something that is intriguing for us, because if you take a plant away from the surface of the Earth, take it to the hills, of course, you can see the vegetation on the hills. Take it even further up in the altitude. I do not know whether they will be having the photosynthesis, because if you even take a plant to the highest summit on planet Earth, you take it to Mount Everest, do you think it will be there'll be a photosynthesis process? We are not sure about it, because the temperature is going to be very different. The ingredients that you need are going to be different. So there is a lot more to do to understand the chemistry, what you see on the surface of the Earth, whether it will happen at different altitudes on our own planet. We do not know. However, if you look at few reactions which are not naturally there on the surface of the Earth, which are artificially made, for example, the internal combustion, where we use the fossil fuels and air is let in so that they burn to give a lot of other molecules. Hydrocarbon, oxides of carbon, of course, nitrogen, because nitrogen is also a constant of air. So certainly it is going to burn. It is going to engage in the reactions. It's not burning. It's engaging in the reactions, the available atoms, and then makes oxygen. Eventually, the carbon that we have from the fossil fuel is going to trouble the engine. Of course, the soot that is made, the residues that are made, that is going to be the product that we are concerned. We are a lot concerned about even after the release of toxic gases. Well, but this is a reaction that we are looking at inside a closed compartment without electromagnetic. The last one we saw was the photosynthesis, is created by the photon, but this is artificial combustion. It is the combustion process. And the worry for us is the particles that are coming out. So the residues we get from the fossil fuels, do they contain allotropes of carbon? Maybe yes, certainly. But when you say carbon is making some residues and so on, can this be happening or a similar process is happening in deep space? May be possible, we do not know. But if we take data from space and we compare the data what we have from this from the burning fossil fuels and so on, then it suggests that it suggests I should have added the reference here from one of the famous paper from Alamandola and Dealing, who started the area of astrochemistry. They've compared the residue from auto exhaust and the Milky Way, and you can see the comparison here. There are quite good. What you see here is the Raman spectrum. So some sort of chemistry that is happening on the surface of the planet Earth. I do not know whether it's only with the fossil fuels. It can be happening even when you burn food. Food burning also gives you a similar carbon content. Something that is very fast in making a carbon suit, because you have to wait for a long time when you want to burn the wood. But if you light the camphor, just a few centimeters of flame, you can see the carbon particles flying through. So even here we get the hydrocarbons, we get the oxide of carbon, oxygen, and eventually the particulate matter. And we are looking at the products which are more or less similar to what is happening in the IS. Something intriguing. Or we looking at chemistry that is due to biological activity? Certainly not, but due to biological activity. Right. So we have uh, looked at a few reactions on the Earth's surface. Now let us move the Earth's atmosphere. But before we move to the Earth's atmosphere, I would like to point your attention to the word ice. When we use the word ice, what comes to our mind immediately? Of course, it is water ice. But if you talk to some people who does handling of cryogenics and so on, they would say that ice, okay, you can say it is also carbon dioxide, dry ice. So this is what we know for the word ice. But if we are going to look at the chemistry and we are going to discuss about the regions of space, then the word ice, it refers to any molecule that is how the astronomers describe it. Any molecule that is frozen wherever the temperatures are very, very cold, cryogenic conditions. Now, after a brief look at this word ice, we move back to the Earth's atmosphere. I will link the word ice later coming up. Chemistry in Earth's atmosphere. Of course, there's a strong coupling between our surface and the atmosphere, so that there is a lot of influences due to that. But we will again move on to a particular reaction, the two-step reaction. See here, plenty of oxygen in our atmosphere, photons from the sun are absorbed by the oxygen molecules. Eventually, the energy is spent to break the bonds in the oxygen molecule. An oxygen atom becomes available. Two oxygen atoms available. Now, the combination of an oxygen atom with an oxygen molecule in the presence of a third body, because we need the third body to take out the excess energy, that is reaction, synthesizes the ozone molecule. Ozone, of course, many of us, maybe all of us knows that it is the molecule that is protecting us, molecular blanket, which absorbs at the similar wavelength where the DNA in our cells. Certain ozone, we risk the absorption of UV photons by our cells, by our living cells. Right. At the same time, ozone is also thought to be a biomarker because on planet Earth, to make ozone, we need a lot of oxygen. A lot of oxygen came from the biological activity in the past. Then, when we have sufficient amount of oxygen, ozone blanket start to be playing a role where the flora and fauna. So there is a blanket which is saving us from absorbing the UV radiation. Same time, molecule can be considered as a biomarker because of the biological precursor. But if you find ozone elsewhere in the solar system, can we say that those places harbor some biological activity? Is it possible? Or do we have any abiological activity, abiotic chemistry that is happening? We are going to look at that. Chemistry in Earth's atmosphere strongly driven by the absorption of photons, molecules. But in the electromagnetic spectrum, if you see the different wavelengths, which are the different energies, when they are getting absorbed by the molecules in the atmosphere, we have different processes that are happening. One particular effect that we are trying to understand a lot, generation of secondary electrons. Molecules get ionized, we get the electrons kicked off. These electrons can initiate chemical reactions. Secondary electrons, energy of course, there are some thermal electrons whose energies are less than 1 eV. So we are now looking at a new player in the chemistry happening in the atmosphere. Subsurface or on the surface, we talk about electrons. We move to the atmosphere, photons are absorbed by the molecules. We are now starting with a new player and initiate them. So it is good to have an atmosphere, certainly yes. And depending on the height, we have different processes going on. But we are very much interested with these electrons because the moment you move away from Earth's atmosphere, okay, the protection layer is gone. Now, any object which is away from the Earth's surface will face the entire electromagnetic spectrum. So the closest surface to us, or the object to us, where we can examine this, none other than our own surface. Moon surface does not have the protective atmospheric protection that we enjoy here. So all of the sun's energy are getting to the surface of the moon. But what could be the term we can use? It doesn't have an atmosphere. We can say it is an exosphere, where the density of molecules are very, very low. So the molecules do not collide that easily. They are far apart. Right. So this will have some problem and some advantages as well. Problem is that if an astronaut goes, he cannot easily breathe because there's no atmosphere and so on. But the advantage is that the chemistry is going to be rich because you get a lot of energy coming to the surface. So we all know a decade before the finding from our Chandrayaan-1, where the water molecules are there almost everywhere on the moon. Synthesis of this water comes from either from the proton impinging on the minerals on the surface of the particles on the moon. Then they synthesize OH radicals, and this OH readily combines with the hydrogen atom to make water. Nice. But water is not that much, it's a little, but still it's good, no problem. Water is there, that is important. This water molecules, because of the temperature, the surface temperature of the moon, they cannot be, they are not going to be on the surface of their host dust. So they start moving, they start hopping around. They start hopping around until they find a place where it is cold enough so they get stuck. So do we have this cryogenic trap for the molecules to stick and stay for a long time? Is it possible to have them? Because moon does not have an atmosphere. On planet Earth, if you take the atmospheric pressure 1 bar and you have the water ice, okay, at 1 bar, you can have water ice until 0 degrees centigrade, no problem. But the same water ice, if you put it in vacuum, 0 degrees centigrade, there won't be any water ice, rather it will be in the gas phase because the vapor pressure builds up. So the temperature of water ice has to be much lower and lower. Okay? it has to be at least below 150 Kelvin, so that even at 10 to minus 10 millibar or so, the layer of water molecules can be there in the ice form, right? So do we have these cold traps? Certainly, yes. If you go to the poles of our moon, to the south and the north pole, we have a lot of permanently shadowed craters. Permanently shadowed craters. These are the places which are created by the incoming hypervelocity bolides, or called the meteorites, or even not, because the size of the crater tells you that these are large chunks of leftover material, the asteroid belt and so on. They impinge on the surface and create uh, the loss of material creates a place where sunlight is unable to reach, because the depth is so much that sunlight cannot reach these places. The moment sunlight cannot reach these places, the temperature is going to fall. Now, when this is happening for a long time, the temperature is going to be lower and lower, and it is going to trap. It is kind of a refrigerator, you can say in terms. It is going to trap the molecules that are coming to these places from hopping from the hotter areas of the moon. Is this only one crater? No. There are so many craters on the moon which are permanently shadowed, so they harbor a plenty of molecules in the ice phase. Now the word ice comes in. It is not just the water molecule. Water molecule is one example. They harbor plenty of other molecules as well, depending on the temperature until which they can stick to the surface. Now, so we talked about the water synthesis. What if same ingredients that we looked at on the surface reaction of our Earth for the photosynthesis, water and CO2, they are present surface of the moon, because we said that it's not just the water molecule in the ice phase, it can be other molecules also. On the moon, we know that plenty of water is there, and of course, good amount of CO2 molecules are also present in the ice phase. If they combine, and if they are processed using the photons or the protons or whatever the ions that are coming in, they tend to make carbonic acid. Right? The laboratory experiments clearly show that carbonic acid is one of the major products. Now the question is, for the photosynthesis, we got some sugar molecules from the photosynthesis, got the sugar molecules, but here we get we get carbonic acid. Of course, there may be other products as well, but I'm listing the major products, one of the major products. So can we call this a molecular complexity? Because you're starting from small molecules, you're building up and going towards a larger molecule. Yes, certainly. Why not? But is there a difference, or is there a well-known definition, or even some sort of a discussion to say what is a simple molecule and what is a complex molecule? You move away from Earth. Right. So we know that an atmosphereless, airless object, plenty of that can happen, and your chemical complexity is going to grow even there are no biological activity. Let's move slightly to the other part of our inner solar system. Our inner solar system has objects that are hot and cold. If you take Mercury and Venus, these are the planets which are very, very hot. Venus is the hottest because of its low atmosphere. And Earth, we don't have to Earth. You move away from Earth before the asteroid belt, you got Mars. For example, if you take Mars, Mars is somewhere in between an atmosphere and the exit, because the pressure on Mars isn't as good as what we enjoy on planet Earth. Same time, it wasn't as bad as Moon without any atmosphere. It has got a good amount of, I think, 1/10 of the atmosphere of Earth. But the major molecule that is present, CO2, and a bit of water is also there, but CO2 is in plenty. So if you look at the reaction on the atmosphere of Mars towards the ozone synthesis, which is required if anyone wants to live on the planet, have an ozone blanket so that you don't get the cells are not going to, the DNA is not going to absorb the UV photons. Certainly, yes, we need ozone, but how to make ozone on Mars? We don't have a lot of oxygen like Earth. No problem. The carbon dioxide concentration, whatever is present today, Mars is losing the atmosphere, so whatever is present today is capable of making ozone via this reaction. What you see on the screen, carbon dioxide absorbs the UV photon, associates carbon monoxide, and releases an oxygen atom. Of course, this carbon monoxide also in turn absorbs the UV photon, and it will also release the another oxygen atom. But let us take, not to go into the complicated mechanism. Let us take this simple equation. The release of a single oxygen atom now enables us to make molecular oxygen. This molecular oxygen combines with another oxygen atom to make ozone. So eventually, the efficiency isn't that good as having an oxygen atmosphere, but we'll be able to make ozone. But are these ozone molecules present everywhere on the planet? No, it's not like a blanket what we enjoy here. Rather, it will be in a localized entity because we are not having a good concentration of CO2. Right. So we are away from the sun. Mars is certainly away from the sun. So okay, we can say the temperature is low, so there is no wonder having molecules in the ice space. But what if we say that you have molecules present in the ice space, and that place is very close to the sun, none other than our own planet Mercury. If you look at the polar regions of Mercury, where again, similar to what happened with our moon, the impact takes off a lot of material and then leaves the leaves leaves a depression where the sunlight is unable to reach. So irrespective of however how much the object is close to the sun, does not matter. As long as the sunlight does not fall, there is no heat. There is no heat, certainly the temperature is going to go down. That's what our microwave background explains. If there is no heating source, then the object keeps plunging towards the lowest of temperatures, can go up to 2.7 Kelvin. Of course, it doesn't reach that much, but it can go up to that much. That's what we know. So the temperature is going to fall even on planet Mercury when sunlight is not present. These are the places where the molecules that are hopping on the surface of Mercury go and make an icy layer. Then it's not just water or carbon dioxide molecule, it can be any molecule. Okay. Nice. So there are ice close to the sun. What happens if you move away from the sun? You know the temperature distance relation. If temperature proportional to 1 over root d, root of the distance sun. So the temperature is going to fall a lot. But in these in these craters where sunlight does not fall, the chemistry is initiated by electrons, energetic electrons, protons, or even ions, some other ions. So now we are moving far away from the sun, the outer solar system, and at the in between the Mars and Jupiter, of course, we have these asteroids. And asteroids again feel the same thing. The surface of asteroids are processed similar to the way of like our moon. And if the asteroid surface temperature is lower, then some of the product will differ. Right. We are now into the outer solar system where temperatures are very, very low. When you say the outer solar system, there is plenty to look at because every planet in the outer solar system itself is a mini solar system. For example, Jupiter, you take, there's plenty of satellites and so on. And then surface of these satellites are frozen. They have the icy mantle, molecules that are present, they experience the same sort of impacts, that the same sort of processing that is happening due to hypervelocity impacts and so on. But what happens on the moon is on a target which is made of minerals, a lot of high temperature surfaces. But whereas on the icy moons, we have these icy molecular layers taking up these impacts. So there is a big difference between the chemistry. And what are these layers made of? Mostly, if we take the first moon of Jupiter, Io, it has a lot of sulfur and sulfur oxides. And then moving away from Jupiter comes Europa. There are dedicated missions going to Europa, both the NASA and the European Space Agencies, study the icy moons of Jupiter. And then comes Ganymede, Callisto, and so on. There is something interesting for us here. If we look at the moons of Jupiter and a few moons of Saturn, you can see ozone present even on these icy moons. Few slides back, we are discussing the process. If ozone is present on Earth, can we consider that as a biomarker? We can look at ozone elsewhere, and we can say, oh well, there could be life there in those places. But these icy moons are very small to have an atmosphere on their own. So, what was the reason we see these ozone molecules? Similar to the equation what you saw for Mars, these ozone molecules are made from the oxygen-rich molecules that are present, like SO2. There we saw CO2, here it is SO2. So the oxygen atom that is released, responsible in a two-step process, make ozone. Similar way for Ganymede, we have CO2, we have SO2, and so on. For Dione and Rhea, they got CO2 as well. So the precursor for ozone can be a molecule which is rich in oxygen. Definitely, then we'll make some amount of ozone because the concentration will be very different. Right. So we just saw that many icy moons are present. Let us take a look at a few of these. Whatever is given in J here, they are the moons of Jupiter. Whatever given in S are the moons of Saturn. Okay. Rhea and Dione of Saturn. Jupiter, we have Europa, Ganymede, Callisto. I will input Io here. Quite small when compared to these. In interactive sessions, I used to ask this question, but here I will just go through. What you see here, or what you see in this slide, are the moons of Jupiter and Saturn. But what you see in this slide, it may appear like the photographs of some satellites of the solar system or so, but they are not the satellites of the solar system. Rather, these are the underside of the frying pan that is used for cooking. So you can see the different texture, the different colors, and so on. These come from the different chemicals that we use. Of course, the masalas that we use at home and so on, they differ in their color and, of course, the chemical compositions. So, is there anything similar when you talk about the surface of the icy moon and the analog which I was like showing you? Certainly, yes. So you need to have a source which is responsible for the different chemical compositions on the surface of the icy surface. That source is something interesting for us because we didn't see this for our own Earth. We didn't see this for our own moon. Okay. Of course, our moon gets into Earth's magnetosphere and goes out, but this happens in an effective way for the icy moons of the giant planets, where the magnetospheres of the giant planets, they act as the painters, where they are like transferring the chemicals from one moon to the other. For example, you have Jupiter here. Io is full of sulfur. It picks the sulfur from Io, and the sulfur ion is taken by the magnetosphere to the other moons of Jupiter. How the sulfur ion is picked up? First, the UV photons will ionize the atom. Then, once the atom is ionized, the magnetospheric particles pick these, and then they are accelerated. And the surface composition of the other moon, say for example, if they have water and CO2, and when the sulfur ion goes, it can make a lot of sulfur oxides and so on, which is the initial reaction. But over a large time scale, you can see they start making complex molecules. Okay? So the entire process starts with the magnetosphere picking these ions. So there is a chemical transfer going on. And this, of course, is a new player again for us. Whatever we saw for the Earth's atmosphere, the electrons come into play. And then for the moon, of course, we have everything from the sun, being electrons. We move away to the outer solar system, magnetosphere has a major role in affecting the chemistry of these dicey moons. When you move to the Saturnian system, things aren't different. They are almost the same, like what you see in the Jupiter system, with some small difference. Because the Jupiter icy moons, they do not want, none of the moons are having a good atmosphere like the moon, one of the moons of Saturn, which is Titan. So, for example, if you take the planet, for example, if you look at the alignment of satellites, the Saturnian surface, Titan is further away. That's Titan here. Then you have Rhea, Dione, and so on. This is then Philadelphia. So Titan being one of the rich moon in terms of atmosphere, we'll put it in that way. We're not going to the atmospheric chemistry of Titan. Titan has a lot of nitrogen and so on. The plasma around Titan will be rich in nitrogen ions. These nitrogen ions are picked up and they can be transferred to other moons. What you see here is it's a cartoon of the Saturnian system also. For the next picture, we'd like to show you. This is a real picture from the Cassini spacecraft. It may look like a graphic, but it is a real photograph from Cassini. Saturn is behind this moon. This is Rhea. You can see the quintet of moons here. That's what you see the Saturnian ring. So the Saturnian system is said has the moon with a lot of atmosphere, rich in nitrogen. What is known to date is that the chemical transfer between the moon can also influence the surface chemistry of another moon. This distance is not much than twice that moon distance. Saturn is on the other end of it. So you can say that there are many players if you move away from the Earth that can start the chemistry. And we are in a time that we have understood not much of it. We have understood one maybe a small portion of it. So we need a lot of more spacecraft. We have to understand the flux, the amount of particles that are available. Eventually, we need dedicated space mission that goes beyond Saturn. So far, we have been exploring Jupiter and Saturn to some detail. Even that is not sufficient. And of course, we have gone towards Pluto and so on. But in between, we have the other two planets, Uranus and Neptune. Dedicated missions are needed to understand the chemistry that is going on in these other objects, other planetary system, other mini planetary system in the outer. Right. There is something common if you look at all the moons, whether if it is the inner, it is the moon of the inner solar system object, or it is the moon of the outer solar system object. The common process, apart from these cosmic rays, of course, the cosmic rays is there everywhere, that the impact of objects if they intersect the path of another solar system body, then they are going to be in the collision course. This collision course is going to be a problematic situation if it is with Earth. Hopefully, it is not much with Earth. I mean, not the larger objects that are colliding with. Of course, we have these tiny ones, and sometimes even foot-size objects that enter Earth, and we get these meteorites on the surface. Of it is burnt in the atmosphere. But if you look at the surface of the moon, there are it is heavily cratered. The icy moons are heavily cratered, and the sizes are quite big, and so on. So impacts are inevitable. They are everywhere. But what will be the difference if you look at a process that is initiated by the photon, electron, or a incoming ion, and so on, with respect to this impact? The other processes mostly brings in the chemical changes where the energy is taken by the bonds, and these bonds break to make new molecules, or even a larger molecule will dissociate to the small fragments. But an impact is not like that. It does affect the surface. Chemical changes are also there, as well as we see the physical changes. That's why you see a crater there. The chemistry at that moment when an impact happens is definitely present, because the energy is being spent on these molecules, or even uh, given the energy amount we are looking at, we are talking about even micron sized particles that are being chemically altered. Okay? Thanks to our colleagues at the University of Kent in UK, we have carried out some experiments. I would like to run this video for you so that I'm trying to play this. Okay. All right. So what you saw, an IC target, which is at around 200 Kelvin. That target receives an incoming 1 to 2 nanometer size stainless steel bolide, and the velocity was about 5 kilometers per second. I'll play it again. So you can see here, okay, physical change that is happening. You are losing a lot of material when the impact happens, and if you take that ejecta that is coming out of that impact, a lot of chemical changes have happened. That ejecta, whatever is coming off is the ejecta. Okay, then the physical changes happen to the target. Those areas, if you take some sample out of it, they also have this chemically altered material. So for a 5 kilometer per second, you can say that these things are happening. In the real scenario for airless body, we look at velocities from 15 kilometers to up to 70 kilometers per second. So you can imagine the amount of energy that is getting dumped. Okay, right. So chemistry can be initiated in many ways, not just particles that we don't even see with our eyes. You can see the particles that initiate chemistry with your eyes. The bigger ones, the impact. Right. Now we go to the edge of the outer solar system. We go to the Pluto, thanks to the New Horizons team. We have pictures of Pluto in front of us. So when we are in school and colleges, for us Pluto means a speck of light, which is there. If you look at a lamppost from a faraway distance, look at the light on the post. And Pluto was something like that, even for the powerful telescope of that time. They have to go closer to it to see how it looks. What you see here is Pluto and Charon. Right. So when you move away from the solar system's influence of the solar photons, well, the temperature is going to drop, as we saw before. And now the temperature is further lower. That the average surface temperature of Pluto not more than 35 Kelvin. 35 Kelvin, you can convert it to degree centigrade. You will know how low we are. Right. So molecules are there present even on these places. These molecules you see are now dominated with the presence of nitrogen. That's where we have the sublimation temperatures coming into role. On Pluto, they have discovered mountains that are made of water ice. Because water ice at 35 Kelvin will be much harder than a rock. But what will be the other ice which will be present here? Well, it is the nitrogen, the oxygen. What you see on planet Earth for the temperature we have here, nitrogen and oxygen are in the gas phase. They don't freeze. But the same molecules, if you introduce it to Pluto condition or so, they can freeze. And they make the ice. Pluto contains a lot of nitrogen, a little bit of methane and carbon monoxide, and a little bit of other constituents, including water. Something interesting about Pluto is that Pluto was explored when the spacecraft was going towards Pluto, New Horizon. We know there is only one moon for Pluto. Then later they discovered that in fact there are 4 to 5 moons total for Pluto. Right. So there's so much to understand. If you look at the Pluto, because the color difference, you can see some places are very bright and some of them aren't. The same was there for Charon. Places are brownish and some of them are not that much covered with these particles. So chemistry is playing a role. And what brings this color? Like you said, the painters. In this case for Pluto, the painter is not a magnetosphere. Pluto does not have a magnetosphere. Till now, we do not know it. It's mostly the effect of cosmic rays. Of course, there is some solar photon process there, but majorly it is through the cosmic rays. When you extreme low temperatures, the question I put to the people, school and colleges, you are very well you're very well aware of the Arrhenius equation that talks about the rate constant with respect to temperature. So I leave it to you figure out whether we can consider this equation if we talk about reactions at very low temperature. Right. We saw that Pluto and Charon, we are further away from the sun, lot away, several tens of AU. 1 AU is the distance between sun and Earth, right? So it is several tens of AU away from the sun. We see this brownish color, on the surface of these. Of course, the chemical reaction left over from a chemical reaction. What we have seen from the wood burning or from the auto residue, the vehicles from internal combustion and so on. But here, Pluto and Charon and the object that is further beyond Pluto and Charon, we are into the Kuiper belt. Even this smaller object has something similar. It is also slightly reddish in color. And we are again lucky. We just didn't look at only the Pluto and Charon photograph, but we are lucky to witness the object Arakoth, which is the name given by NASA for the object that have explored in the first exploration with the spacecraft of an object in the Kuiper belt. So the chemical composition is somewhat different here because you don't see that much of reddishness in other icy moons. The similar way what we see with Pluto, Charon, and the object that is much beyond. Here, I'd like to point out that this is the pristine region of the solar system where the long period comets originate. So they contain a lot of nitrogen, oxygen, carbon monoxide. A lot of the simple molecules are present in these objects. But the question is, when they explored this object, they didn't see much of water on the rock surface. So the conclusion is that water would have combined with methane by the action of cosmic rays would have converted much of that into methanol. Some of them would have gone to make some hydrocarbons, and eventually some residues. Right. So every object is unique. What we have seen so far, it is very hard to come to a general conclusion. Okay, this will be the final chemical composition of a certain region in the solar system. It is very very difficult. What we have seen as of now, we started with planet Earth. We moved to the objects in the edge of the outer solar system, from the inner edge of the outer solar system towards the outer edges. Now we move deep into the space, beyond the solar system. We go further the zone which is available for the formation of a new star, the interstellar medium, where the temperatures are very, very low. The processes are going to, we are going to see that initiate the chemistry are not similar to what we have seen so far, but some of the sources are same, like the cosmic rays. I'm sure that everyone would have gone through this equation or school textbooks. So equation you can work it out, change the temperature and pressure. Of course, you are into the different regions of the interstellar medium. Temperature is quite low when you talk about the density, which is very very high, and the UV photons are unable to reach. Temperatures drop quite heavily, up to 10 Kelvin. Wow. So if the densities are very low, how can we have a reaction? Similar thing what we looked at on the surface of the moon. Moon does not have an answer. So the reaction is going to happen on the exosphere. No, it is going to be very difficult. Rather, it can uh, the reactions we can expect to happen on the surface of the moon. So there is a surface. But do we have any surface in the interstellar medium for these reactions to happen? Certainly, yes. We have some places. These are the solids, dust, the dust particles. The chemistry in the interstellar medium is either gas or solid, not in liquid phase, because the vacuum of the interstellar medium is very, very low. So molecules in the liquid form are not possible. Either it will be frozen under the surface, to the surface of a dust, or it will be available in the gas phase. When you say when you see the dust, just show you from the uh, Stardust mission, they collected the dust that comes out of a comet. Spacecraft went through the comet tail, and then there's one of the dust particles that you can see here collected. So interstellar dust, you can say, is somewhat similar to this. It's very fluffy and random in general, but there are also dust particles that have a definitive shape, because even crystals can grow. But the dimensions you are looking at the dust are not more than a few microns. Of course, most of the dust are in the orders of a few tens to hundreds of nanometers. Okay? But how this dust helps us for the chemistry? These dusts which are very, very cold, like you saw in the case of Moon or Mercury, the molecules, when they stick, when they hit the place where it is very cold, uh, they will stick to the surface of this of the dust or the cometary circuit or something. Then they start making the more number of molecules that come, they start making the layers. Nice. This is where the dust plays a major role. Cold dust starts accumulating the molecules and it makes an ice. Again, as we say, the ice, the word ice, not just water or CO2, can be ammonia, it can be methane. Okay. So we have this icy mantle on top of a dust core. How the chemistry happens? You need some energy, yes. Cosmic rays, UV photons, to some extent. Energy is coming in, no problem. If you look at the abundance with respect to hydrogen, we have the reacting atoms, good numbers. Helium we cannot consider because it's not going to take part in any reaction. course, hydrogen is going to react, so that is going to be the driving force. That's why you see a lot of hydrocarbons and all that, nitriles and ammonia and so on. So the dust surface is now providing us, like you can even call that as a chemical factory, where the molecules or atoms diffuse, then react, and then they go off on the dust surface depending on the temperature. This is the sublimation, similar to the analogy that we have seen for Earth. Nitrogen and oxygen is in the gas phase, for Pluto it's in the ice phase, and so on. So the sublimation temperatures of molecules are very, very important. Right, we say this chemistry is happening on these few tens or few hundreds of nanometer size dust grains. Is that very efficient? Can this lead to molecules that are quite large? Yes, maybe. Why not? If you look at the discovery of molecules to date till the 2023, there's plenty of them, more than 250, I think. This plot, what you see, is up to the year 2010. There's a reason behind this. You see this plot here of 1940s. There's a huge gap towards the discovery of another molecule. Then the moment water and ammonia were discovered, that's the time plenty of molecules were discovered in the interstellar medium. Then eventually in the time stamp, you can see simple molecules that we know are also found. But something interesting here, you see oxygen and nitrogen were found at a later date. You know, oxygen and nitrogen has to be there. They are the simplest of molecules, but it is the reason behind the later detection is because of sophisticated instruments, detection techniques are quite important, because some of them may not be that easy. Find a molecule of water is quite easy, of ammonia is quite easy than finding an oxygen. So the detection techniques matter. Eventually, you see at some point of time they found one of the largest molecules, C60 and the C70, which is called the fullerene, the Buckminster fullerene, which we know quite well, in fact, because it resembles the football. Right. So the chemistry in the ISM is much richer than we anticipated. Too many molecules, and they are discovering plenty of these. One more interesting factor, if you see, yeah.
It's almost 4 o'clock.
I'll be finishing. I'll be finishing another few minutes. So the interesting point, you see, when water was discovered, it was exactly 1969 when Armstrong was stepping on the right. So plenty of molecules are there. The chemistry is much richer than we expected. How many molecules were discovered just the year after the lockdown, 2021? They found nearly 41 new molecules. Now this is adding a lot more to the complexity. Because I have stopped here at 2010. You don't see that other one. Otherwise, the curve will be going a lot steeper. Plenty of molecules to be identified in the near future as well, because we are having powerful telescopes than the past. The detection techniques far better. Right? When we talk about interstellar medium, we cannot include the comets, because the interstellar medium is where the solar system is made. Look at the comets. Yes, a lot more molecules are present. Cannot name a few, because whatever molecules you find in a comet is what you find on planet Earth. Cometary molecules is what is thought to be responsible for life to start on planet. The comet is called the postmasters. They of course take the molecule around different objects in the solar system. So when we talk about molecules in the interstellar medium, what is a simple and a complex molecule? I was posting this question earlier in the talk as well. So the moment you hear this question, first we have to see whether it's the planet Earth or other parts of the solar system or the interstellar medium. Planet Earth or other parts of the solar system, yes, simple molecules are something like water, methane, ammonia, and so on. But if you talk about the deep space, then we do not know which could be a simple molecule, which could be a complex molecule. Because even a 4-atom molecule, for example, methane is a simple molecule for us. That's only 5 atoms. But if you have a 4-atom molecule, we are unable to say whether it's simple or complex because of the formation mechanisms. All 4 are different atoms. Okay. Chemistry in the interstellar medium, not just of something that happens only at the low temperature. Of course, the high temperature as well. Where you see in the first slide, we have given greater than 10,000 Kelvin and so on. Can be happening. Sorry, there are processes that are happening which elevates the temperature of the surrounding to several thousands of Kelvin. We don't want to go into that part of the astrophysics side and so on. So the regions that are of high temperature now adds more problem for experimental people, I should say, because the pathways that are going to be involved in chemical reactions are going to be many. The moment you look at a high temperature process, it may simplify, but usually the pathways are quite a lot depending on the ingredients that you begin with. So we are looking at several pathways. We start with a certain material as the molecule, you say, can be the low temperature, or you look at the residue, which is at the high temperature. High temperature, even room temperature is high temperature in the interstellar or the solar system context. It depends on the zone where you are looking at the chemistry, right? We are looking at plenty of things, but all these things are looked at to understand how life started. This is where we will end if we understand how it is made. Because yes, molecules, of course, you take molecule A, B, C, D, it can make some other molecules, and if you again give some energy to that, it can dissociate and make A, B, C, D, and so on. It keeps doing this. What we do, I'll be finishing another 2 minutes. What we do to understand this, we bring in the condition, as I said in the first slide, we bring in this condition of space inside the laboratory and use this molecule, use different sources, even starting with the electrons, the simulate the photons from the sun, the V photons, and even we are going to start looking at the X-rays. Impacts are also there, ion sources, and so on, where the energy that is spent on this molecule and what are the products that we can get. We do not know. The simple molecules can sometimes make the largest chain of them, depending on. Start with, for example, if you take this carbon, it can make the fullerenes. When it can make a graphene even at 10 Kelvin. Not the normal temperature, what's the laser or so, the lowest of temperature. This slide, what you see in PRL, we do have a database for the low temperature study of these molecules. You can go through it. How we simulate these in the laboratory, we bring the condition inside a small chamber, where the small chamber is cooled down to lowest of temperatures using liquid helium, compressed helium, liquid helium. Then with the action of combined action of turbomolecular pump, the vacuum pump, you can generate ultra high vacuum. This is quite close to the interstellar condition, not exactly the interstellar or the solar system object condition. Then you can bring in the dust of the interstellar medium where the molecules can stick on it, or these icy satellites of Jupiter, that's Europa on your screen, or even the surface ice of Mercury, or even the comets, or even the surface of Mars, you can simulate to some extent, and everything in common here are the molecules. Right. So there's another version of it. We just want to show you how it is done. The virtual thing. So the chamber is there, which is at very low vacuum. Then the window that you have here, which is given here, okay, that's the window that acts as the dust. It is the infrared source is used, and why we use the infrared source? Because it's a non-destructive technique. The photons, the wavelength of infrared photons will be absorbed by the molecules, so they vibrate, but they don't dissociate. Okay. We are not disturbing the chemistry that's happening because of energetic particles. We can attach electron gun or an ion source or even a VUV photon source to this, so that you can look at particular process. You want to simulate if you want to simulate the process, the chemistry in the inner solar system or the outer solar system or even the interstellar. High temperature process, we simulate it using a shock tube. This shock tube is mostly used for astrochemistry experiment. The dedicated shock tube for astrochemistry is about 7 meters long. We go to the Indian Institute of Science. There's a huge lab, and Professor Arnon and his collaborators use shock tube to study some of the reactions in the interstellar medium as well. We have named the PRL shock tube as ISTA. We go to the Disney, the Tarzan, there's a snake, that there's a character named as ISTA. If you take a shock tube or a snake, there are more or less equal. Disney says ISTA destroys everything on the way. If you look at the shock tube or the shock wave, of course, it is also destroying everything on the way. Whether it's destroying or it's making depends on how we take it up. It of course makes it is not just destroying. It of course makes some of the useful products for us to understand the origin of life. For example, if you take amino acid and put it in front of a shock wave, which is of Mach, which is very strong, 5 Mach, high times the speed of sound, the temperatures we are reaching, the gas temperatures we are reaching about thousands of Kelvin, 7,000 Kelvin. This all happens in a 2 milliseconds. That's what you begin with. And that's what you end up with. Very different. Now, you look at the you analyze the product that you've got, which is because of the high temperature process. The temperature chemistry that has happened at very high temperature. For example, if you take these 4 amino acids, aspartic, arginine, glutamic, and lysine, and shock it, get a lot of things. One particular thing, what you see, the polypeptide. Not just a polypeptide, rather you see the architecture that is there, the chemical reaction, like you said, the physico-chemical changes. Okay, so the chemistry is important, yes, but when it is combination of a physico chemical nature, then it is helping us to move towards a step further into the origin of life to understand how life would have originated. So there you can see an architecture here, which is very complex. At the same time, it is all done in within a in just a few milliseconds. So, what is the importance of astrochemistry? Yes, we are looking at molecules that can form life, the molecules of life, such as the amino acids, nucleobases, and sugar. So, what is astrobiology then? Is it making the first cell, or the complex molecules, or the molecules of life is where astrobiology starts? I leave this question to the audience. I think there's an astrobiology talk coming up, the same program. Stop here. As I said, I am representing a large group of members. I have the opportunity to discuss what you have been going for many years. We look forward to many young people taking up this area of research. Thank you.